So this is day 2 on graphing standard form quadratic functions, which are parabolas. Again, day number 2 or video number 2, whatever you want to call it. Let's jump right in. Yesterday we were working on this page of notes. Yesterday we learned a lot of important things about parabolas. Any quadratic function will be a parabola, a U-shaped curve. And usually we're going to have a standard form, ax squared plus bx plus c, quadratic trinomial function that's going to produce a parabola. We also learned the importance of the a value. The a value is very, very, very important. If it's positive, the parabola is opening up. If it's negative, the parabola is opening down, right? Not only that, if your a value is closer to 0, it gets closer to becoming a line. It gets wider and wider and wider. If the a value grows, like from 1 to a 2 to a 3 to a 5, it gets narrower and narrower and narrower. I hope we remember that from yesterday. So just to review, we graphed this guy yesterday, and we noticed that the a value is negative. That's why it's opening down. And the a value is actually a -3. That 3 causes it to get vertically stretched. So it's a little bit narrower than your regular U-shaped curve. Like compare that one to the original parent graph. That one's a little bit wider. This is the more natural U-shaped curve. This is the y equals x squared. This is the parent graph. And over here, it got reflected. It opens down because it's negative, and it got vertically stretched. It's narrower. So the a value tells you a lot, right? What else did we learn yesterday? We learned that the most important point is called the vertex. It's either the highest point or the lowest point of your parabola, depending if it opens up or down. We also learned that through any vertex, there's a vertical line, and vertical lines are all x equals a certain value. But that vertical line right there is called the axis of symmetry, and that line will be vertical, and it'll pass right through the vertex, and it'll always be the equation x equals whatever the x value is of your vertex. In this case, the x value of the vertex is 0, so this green line is the equation x equals 0. And we use that axis of symmetry to reflect points from one side to the other. And whenever you need points, you could use an input-output table. Plug in 0, 0 squared 0, plug in 1, 1 squared 1, plug in 2, 2 squared 4, and you get coordinates, and you could map them over to the other side, and that's how we graph parabolas. But we did conclude yesterday that there was this quicker method to graph besides using an input-output table. What is that method? Well, it comes from truly understanding the a value. Okay, the a value determines not only if it opens up or down, but if it's wider or narrower, right? So if your a value is 1, kind of like the parent graph that we just did right here, if the a value is 1, then it ends up being this wide, right? It ends up being that wide right there. Okay. If the a value changes, then it might get wider or it might get narrower depending on your a value. But if your a value is 1, it's going to be exactly this width. It can't be wider, can't be narrower. You guys all agree with that, right? Okay. So what does that mean? That means that any equation that has the a value of 1 is going to be exactly this width, not wider, not narrower. Okay. So what does that mean? That means that you could actually use these coordinates right here as if it were a pattern. So instead of them actually being coordinates 1, 1, 2, 4, 3, 9, you could think of them as a pattern 1, 1, 2, 4, 3, 9. Okay? So what does that mean? Once you find your vertex, you'll be able to go 1 to the side and 1 up. And then go back to the vertex and go 2 to the side and 4 up. And then go back to the vertex and 3 to the side and 9 up. 1, 1, 1 to the side, 1 up. 2 to the side, 4 up. 3 to the side, 9 up. Now, right here, those are actual locations, 1, 1, 2, 4, 3, 9. But if you go anywhere else, or a different type of parabola, if your a value is 1, you could use that pattern of 1, 1, 4, 2, 4, 3, 9. So right here, the a value is 1, and let's graph this, and let's use the pattern instead of a XY table. So let's begin by writing down step 1 is the vertex. And the vertex is a coordinate. How do you find that coordinate? Well, you find that coordinate by using the formula for vertex x equals -b over 2 times a. And when you use this formula, please use parentheses instead of the letters before plugging in. So you really have a negative parenthesis over 2 times parenthesis. And where do we get our b value and a value from the original quadratic trinomial? Now, I hope we remember that it's this simple. The a is in front of the x squared, the b is in front of the x, and the c is the number without an x. So what do we have here on this one? We have the a value being 1. We have the c value being -3 because it has no x. What is the b value? There is no b value. So that means that the b value is 0. In other words, you could, if you wanted to, rewrite it like this. So you could rewrite it like this if you wanted to, just so you could clearly see that your b value is 0, right? There is no x term. There's no x term right here. There's an x squared, but there's no x term. So you could write it like this just so you could see that b is 0. So you're going to be plugging in 0 right there in the numerator and the 1 for the a in the denominator. Okay, so what we really have is -0, which is still 0, divided by 2 times 1 is 2. 0 divided by any number is 0, right? So our x value of our vertex is 0. Very important information right there. So once again, our vertex is a coordinate, an x and a y value, and we just found the x value being 0. So we all put 0 right there. Now we still need to find the y. We know the x, so we need to find the y. What do? To find the y?
You plug it in.
Plug it in. Plug it in. So we're going to plug it into this guy up here, or actually this guy, the original, and we're going to be plugging in 0 in place of x. So I'm going to rewrite the original equation. Original equation is y equals x squared minus 3, but we already know that x is really 0, so plug in a 0 into those parentheses, and then do the math. 0 squared minus 3 is -3, right? 0 minus 3 is -3. So what we really have here is y equals -3. And we're talking about the y value of the vertex. So your vertex is 0, -3. Okay, so that's the most important point of any parabola, the vertex. Let's graph that vertex. 0 on the x, -3 on the y. It is right here. Now, the very next thing that we should always do is find the axis of symmetry. The second thing would be the axis of symmetry.
That's the big line, right?
That's the vertical line passing right through that vertex. Now, it's easy to draw, but in addition to drawing, I will also want you to write the equation that produces the vertical line that passes through the vertex, and that will always be simply x equals the x value of your vertex. What's the x value of our vertex? 0, right? So we're going to put that 0 right there. There's my axis of symmetry equation, x equals 0, right? Now, visually, that axis of symmetry line is important because whenever we get more points, we'll be able to map them over to the other side, reflect them over to the other side. So we need some points, right? We need some coordinates so we could actually reflect it to the other side. So one option is to make an XY table, plug in a number, do a bunch of math, get out an answer, plug in another number, do a bunch of math, get out another answer. But since I know that this A value is 1, I know that it's going to have to open up and be exactly as wide or perfectly U-shaped as this one, because this one, the parent graph had the A value of 1. So I am going to use these coordinates as a pattern, okay? So over here, because the A value is 1, I get to use the pattern 1, 1, 2, 4, 3, 9. Okay, so I would like you guys to write down this pattern over and over and over until you memorize it. 1, 1, 2, 4, 3, 9. Now, that means that from this vertex point, this most important point, I'm going to go 1 to the side and 1 up. It's not a coordinate where you go the coordinate 1, 1. No, you go 1 to the side from the vertex and then 1 up. Now, why up? Because the A value is positive. If it would have been negative, I'd go 1 to the side, 1 down, right? But because it's positive, we know it's opening up. So from the vertex, we're going to go 1 to the side and 1 up. 1 to the side, 1 up. Everybody put a dot right there. 1 to the side and 1 up from the original vertex. And then we're going to go back to the vertex and go 2 over and 4 up. So 2 to the side, 1, 2, and 4 up. 1, 2, 3, 4. Put a dot right here. And then we go back to the vertex, and we're going to go 3 over 9 up from the vertex. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, right there. I think that's right. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, whoops, 9, up there. My bad. 1 unit off. Thank you. So let's just scratch that out, pretend that's not there. X. Anyway, we have these dots. We could reflect them over to the other side. And somebody just asked, if A is positive 1, we get to use this pattern every time? Yeah, even if it's negative 1, you could still use a pattern. The only difference is instead of going 1 over and 1 up, 1 over and 1 down, right? Now, if you're thinking, do I always have to go to the right? No, you could have gone 1 over this way and 1 up because you're going to map them over anyway, right? So now that you have these 3 red dots, we could reflect them over to the other side of the axis of symmetry. So this guy right here, that's 1 unit, 2 units, 3 units away from the axis of symmetry. Go 1, 2, 3 this way. You got your dot right there. I want to do it in blue this time. And then this other one is right here, 2 units away. And this other one is right here, 1 unit away. And voila, we have our perfect U-shaped curve. How does that taste?
Is it good?
That's right. Now, if you, like, let's say you didn't, I mean, you don't have to use a pattern. If you really, really wanted to, you could go for an input-output table, and you could plug in numbers, right? Like, plugging in 0 is not that bad in this case, 0. What would it give us? Well, oh, wait a minute. We already plugged in 0 for the vertex, so we got out a negative 3. But we could plug in like a 1. We could plug in a 2, plug in a 3, so on and so on. But you'd have to do the math. And not only that, this one's easy because it's a quadratic binomial. So like it's pretty easy to plug in a 1 right there. 1 squared is 1, and 1 take away 3 is negative 2. So when you do plug in a 1, you get out a negative 2. You could plug in a 2 right there. 2 squared is 4. 4 take away 3 is 1, right? But what are these coordinates? These are dots that we already have. Like, where is the coordinate 1, negative 2? From the origin, 1, negative 2 is that red dot. But we already got it with the pattern. Or you could go 2, 1, and you go 2 on the x, 1 on the y. There it is. But we already had that point, right? So it's a lot faster to use the pattern, especially because sometimes we end up with quadratic trinomials that are a lot more challenging than just a quadratic binomial. So do we understand that if the a value is 1 or negative 1, it's going to be an identical parabola? If you compare this parabola with that parabola, it's the exact width.
Just move downwards.
It's just shifted down. Yeah, that's exactly right. Now this one, it's not the exact width. It's narrower. It got vertically stretched. That's because it had a negative 3 in the front. So could I use the pattern 1, 1, 2, 4, 3, 9 on this guy that we did yesterday?
No.
I can't use the pattern as is because that pattern is specifically for your a value of 1, right? And this a value is negative 3 that we did yesterday. So I'm about to teach you how to use the pattern, but you just have to modify it according to your new a value. Okay, now check this out. What is the pattern that we need to memorize? The pattern is what? 1, 1, 2, 4, 3, 9. Now, these are not coordinates. Well, they were coordinates on the original parent graph, but this is a pattern from the vertex. So you go 1 over, 1 up. But that's if your a value is 1. But in this case, our a value is negative 3. So what does that do to the pattern? You have to modify the pattern by multiplying the second parts of the pattern by negative 3. So 1 times negative 3, 4 times negative 3, 9 times negative 3. Then you would end up with negative 3 right here, negative 12 right there, and negative 27 down there. So your new pattern, instead of 1, 1, it's 1, negative 3. That means 1 over and 3 down. 2 over from the vertex and 12 down. 3 over from the vertex and 27 down. That way you don't have to deal with plugging in any numbers. Okay. So for example, from my vertex, if I did go 1 over 3 down, check it out. 1 to the right or to the left, doesn't matter. 1 to the side and then 3 down, you get to that red dot. you could go back to the vertex and then go 2 over 12 down. Check it out. 2 over 12 down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm at that dot right there.
So you just multiply everything by the A value.
So whenever you don't have an A value of 1, if you have an A value of 2, just multiply the outputs of your pattern by that new A value. So remember, your original pattern came from inputs and outputs, inputs and outputs, inputs and outputs. So if you have a different A value other than 1, you just have to multiply your outputs by that new A value. Then you'll have your new modified pattern that you could use, okay? So there's a couple more things I want to talk to you about before we move on. Another thing I want to talk to you guys about is domain and range, okay? Domain and range. So domain are your X values. Range are your Y values, okay? So, for example, this parent graph, what is the domain? When I say what is the domain, I'm really talking about does the graph exist to the left and to the right? Does it exist forever to the left and to the right? And the answer is yes. So the domain, and technically the domain of any parabola, it doesn't matter if it's a wide one, a narrow one, one that opens up or opens down, the domain of any parabola is x equals all real numbers, okay? So let's go back to the parent graph right here, and let's write down domain, or D for domain. That would be x equals all real numbers. Now, if you're thinking, wait a minute, I don't see this parabola existing over here at 10, but it does, right? All you got to do is plug in 10. What's 10 squared? It's 100, right? 10 times 10 is 100. So at the x value of 10, where's the parabola at? It's at the y value of 100, way off the screen right there. Does that make sense?
Yes.
Okay, so it really does exist forever to the left, just way up there somewhere, forever to the right, just way up there somewhere. It does go to the left and to the right forever. That's why the domain is x equals all real numbers. Now, when we get to range, those are the y values, up and down. So the question is, does this parabola exist up at 100, up here somewhere? Yeah, it does, because the arrows say it goes up forever. Does it exist at negative 10? No, it doesn't. Does it exist at the y value of negative 4? No, it doesn't. Where does this parabola start existing in terms of y's? At 0, and then above. So how do we say that the range, that the parabola starts existing at the y value of 0 and above? You say y is greater than or equal to 0. And that's your range right there. Cool? So the domain will always be x equals all real numbers. The range is up and down. Where's your parabola? It's either above or below, starting at that y value of your vertex. Visually, it's easy to do. Like, check this one out. We just did this one. What is the domain right there? The domain is x equals all real numbers. Doesn't matter if it opens up, if it opens down, if it's really narrow or really wide. All parabolas have x being all real numbers for your domain. How about the range? The range is y is
Less
it
than equal to 0, less than.
is how about this? Does your parabola exist at negative 10?
No.
Does it exist at positive 10?
Yes.
How about at positive 100?
Yes.
Yes, because it goes up forever. But where does it start existing? In terms of y, because range are your y values? At negative 3 and above. So how do we say that y exists, or the parabola exists at the y value of negative 3 and above? We say y is greater than or equal to negative 3. Bless you. Does that make sense? Cool. All right. Now, there's one more thing I want to talk to you about besides domain and range, because we need to state domain and range on all of our parabolas. We need to be able to also state the vertex. Obviously, you need that most important point. We need to be able to state the axis of symmetry, that x equals whatever the x value is of your vertex. And we also need to know how to state the y-intercept. State the y-intercept of any parabola. All right? So how do we find the y-intercept? I hope you remember from semester 1. To find the x-intercept, you set y equal to 0 and solve. To find the y-intercept, you set x equal to 0 and solve. So if I were to set the x's equal to 0 and solve, my answer will always be that c value. So it's pretty cool to know that the y-intercept of any standard form quadratic trinomial will be the coordinate 0, your c value. Pretty crazy. But to find the y-intercept, you set x equal to 0 and solve. So if you actually set your x's equal to 0, 0 squared is 0, negative 3 times 0 is 0, 6 times 0 is 0, 0 plus 0 is 0, plus 5 is 5. So your c value is 5, so your y-intercept should be 0, comma, the c value 5. And it does cross the y-axis at 0, 5. It's that blue dot right there. Make sense? So on any quadratic trinomial that I give you, you could easily, even easier than finding the vertex, even easier than anything else. If it's a standard form quadratic trinomial, how about something like this? Like if I said y equals x squared minus 3x plus 4. And I'm like, does this parabola open up or down?
Down.
It opens up. Why does it open up?
It's a positive.
Because the a value is positive 1, right? So it's opening up. Where would it cross the y-axis? At 0, comma, positive 4, right? The c value, right? 0, comma, positive 4. Anyways, that is a ton of information I just gave you. What I would like you guys to do right now is to get a piece of paper out and actually jot down these notes right here. So what I did on these notes, before even copying it down, check this out. I want you guys to write down notes on graphing standard form quadratic functions, and go ahead and start with y equals ax squared plus bx plus c. And the very first and most important thing that you need to know is how to find the vertex. That's why right here I put number 1. You always start by finding the vertex. And what is a vertex? It's a coordinate. And how do you find this coordinate? You got to know the formula, x equals negative b over 2 times a. When you do this, x equals negative b over 2 times a, and how do you do that? You get the b right here and the a right there, plug them into your formula, work it out, get an answer. That'll be your x value of your vertex. Once you have that x value, then plug in that x value to solve for y, and you'll be able to get that y value of your vertex. So the first and most important thing you need to do is be able to find the vertex. That's why we're jotting these notes down right here. Second and most important thing is find the axis of symmetry, and the equation of the axis of symmetry will be x equals whatever that x value of the vertex is. Okay.
The equation is...
And again, I'm just reading through all these important facts that I jotted down, so you could hear them first, understand them, then you could worry about jotting them down. The third fact, it's not like in order of importance, but the third fact is you could find the y-intercept of any standard form. I guess I should say that. Y-intercept of standard form. The y-intercept of a standard form quadratic trinomial will be the coordinate 0, comma, c. It's the number at the end without a variable, 0, comma, c, right? That's how to find the y-intercept. That's a very important detail. What else? Number 4, if your a value is 1, you could use the pattern 1, 1, 2, 4, 3, 9 instead of XY table. And of course, this pattern is from the vertex. You go 1 over, 1 up, then go back to the vertex, 2 over, 4 up, back to the vertex, 3 over, 9 up, right? Now we also have domain and range of any parabola. The domain of any parabola will be x equals all real numbers. Or you could also use this notation, x equals that r with the double stick, that means all real numbers, right? So the domain for any parabola will always be x equals all real numbers because it goes to the left and to the right forever. Now the range are your y values, and y is either going to be above or below that vertex y value. I should say above or below or equal to. So greater than or equal to or less than or equal to the vertex y value, okay? Depending on if it opens up or down, which you could tell by looking at your a value. And another fact over here is you could modify your pattern to different a values. So if you have an a value of 2, so if a equals 2, instead of using the pattern 1, 1, 2, 4, 3, 9, you write it down, then you modify your outputs, the 1, 4, 9, you multiply those all by that new a value of 2. So instead of 1, 1, it's 1 times 2, which is 2. So 1, 2, 2, 4 times 2 is 8, so 2, 8. 3, 9 times 2 is 18, 3, 18. What does that mean? That from your vertex, wherever it's at, you're going to go 1 over 2 up. And then back to the vertex 2 over 8 up. And then back to the vertex 3 over 18 up. So that is a lot of facts, a lot of truths about graphing parabolas, graphing functions that are standard form quadratic functions. I would like you to, I'm going to pause it, copy this stuff down, and we'll move on in a couple of seconds. Minutes for you, seconds for people watching the video. Okay, I apologize. We are moving on. If you need more time, watch the video, hit pause, and you'll be able to copy down everything you need. Go ahead and flip over the notes, and you should see practice on the back side. I want to look at number 1 and do number 1 together right now. Step 1 on number 1 is to find the vertex. That's exactly right. So everybody should write down 1, write V for vertex, or you could write it out, doesn't matter. But it's going to be a coordinate, and we need to have the formula memorized, which would be x equals negative b over 2a. That's right. And when we use this formula, we're going to put parentheses instead of b and instead of a. And we're going to go to the original quadratic trinomial function to identify the b value of negative 2 and the a value of positive 1. So the negative 2 is going to go right in here, and the a value of positive 1 is going to be right there. And yeah, the minus negative changes to plus plus, which ends up being a 2 over 2 times 1, which is 2, which is 1. So the x value of our vertex is 1. So technically we found the x value of the vertex, which is 1. Now, in order to find the y value of our vertex, we're simply going to plug that in to the original. So plug it in, and plug it into what? Plug it into this. Y equals x squared minus 2x minus 1. Notice that I just rewrote this, but instead of x's, I put parentheses. That's the safest thing to do. And then plug in your values, the x value of 1. Plug it in right there and right there. And when you do this, you could either use a calculator or make sure you do the correct order of operations. Start with exponents first. 1 to the second power, 1 times 1 is 1. And then multiplication right here, 2 times 1 is 2, of course with the minus sign in front. And this minus 1 at the end, just bring it down. So what we have here is really y equaling 1 minus 2 minus 1. So it's going to be y equals negative 2. So we just found the y value of our vertex. The y value of our vertex, negative 2. So that is the most important point of this parabola, the coordinate 1, negative 2. So let's all go to the coordinate 1 on the x, negative 2 on the y, put a dot right here, and yeah, it's going to be opening up for sure. So here's my vertex. What's the second thing I should do? The axis of symmetry. So right below your vertex work, write down axis of symmetry. Now, stating the axis of symmetry, drawing it is way easier because you would just draw a vertical line going right through your vertex.
X equals to 1.
But the equation is x equals whatever the x value of your vertex is, which in this case is 1. So there you go. That produces a vertical line crossing the x-axis right at 1. There it is. X equals 1 is the axis of symmetry. Now we need more points. Now you could, if you wanted to, you could use an input-output table, an XY table. But since we recognize that the a value is 1, that means it has to be perfectly exactly as wide as our parent graph, which the parent graph had the coordinate 1, 1, 2, 4, 3, 9. We're going to use those coordinates as a pattern. So over here on this side, I'm going to write down pattern 1, 1, 2, 4, 3, 9. And this is from the vertex. And you guys mentioned that this is opening up for sure because it's positive. So from the vertex, I want to go 1 over 1 up because it's positive. If it were negative, I'd go 1 over 1 down. But it is positive, so I'm going to be going 1 over 1 up and put a dot right here. I'm also going to be going 2 over 4 up from the vertex 1, 2, 3, 4. Again, from the vertex 2 to the side, 4, 1, 2, 3, 4 up, put a dot right there. And if you go back to the vertex and go for your last part of your pattern, 3, 9, 1, 2, 3, up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm off the graph 2 units. You don't have to do it, but you know what? Just for funsies, I'm going to put it up here 2 units off, roughly. Anyway, what else could we state? We could state the y-intercept. That's pretty easy to do. The y-intercept, where will it cross the y-axis? It's going to be 0, comma, the c value. And the c value is negative 1. So we could clearly see that 0, negative 1 is right here. And that makes total sense. because if we were to map this over to the other side, it'll land perfectly right there. So that's the y-intercept, 0, -1. Really easy to see on a standard form quadratic trinomial equation. It'll always be 0, c. What else? Let's map this coordinate over to the other side. 2 units away, 2 units away. Put a dot right there. And that's good enough to draw our parabola. So our parabola is going to be going right through those points that we drew. Curves back up. And notice it's going to point at that other point that's off the graph. Same thing with this one going up, pointing that way. So what else could we state about this parabola? We could state the domain. What's the domain of this parabola? The domain of any parabola is what? X equals all real numbers. How about the range? Those are your y values. Does this parabola exist at 10 up here?
Yes.
Yes. Does it exist at -10 down here?
No.
No. Does it exist at -3?
No.
Where does it start existing? -2 and above. So how do I say that it exists at the y value of -2 and above?
Equal to -2.
Y is greater than or equal to -2. Perfect. Man, we've stated a lot of things. Actually, let's go back to the instructions. What does it say? It says, please find the vertex, find the axis symmetry, find the y-intercept, graph it, state the domain, state the range. We did all that. We found the vertex with the vertex formula. Then we plugged it in to find the y value. We have the vertex. We actually stated the axis symmetry. We found the y-intercept, 0, c value. We used the pattern to find more coordinates. We mapped them to the other side. We got our domain and range. That is a lot of things to state about one parabola. So I hope we understand it. I hope we're more comfortable with it. Let's do one more, but let's do one where the a value is not 1. I guess we could do like number 3. We're going to begin the same way. Find the vertex. The vertex is a coordinate. I find that coordinate by doing -b over 2 times a. When you use the formula, use parentheses instead of the letters. And your b value is -8, and your a value is 2. So -8 is the b, 2 is the a. So what I have here is a +8, a negative changed to a positive, over 2 times 2 is 4. So our vertex x value is 8 divided by 4, which is 2. So I know my vertex has the x value of 2. I still need to find the y value. How do I do that? I plug it into the original quadratic trinomial equation. So I'm going to rewrite it. It says y equals 2x squared minus 8x plus 5. All I did was rewrite it, but instead of x's, I put parentheses. Why parentheses? Because I know what x is. X is 2. I'm going to put the 2 right in those parentheses. So I have a 2 right there and a 2 right here. Now it's time to do some math. So let me zoom in a bit. And I'm going to begin by doing 2 squared, which is 4. So I have a 4, but I still have the times 2 in the front, which is 8. That's right. And then over here, I have a -8 times 2. That's a -16. And then I'm also going to bring down this plus 5. So what I really have here is y equaling 8 take away 16 is -8. -8 plus 5 is -3. So I just found that my y value of my vertex is -3. That's the hard part, guys. Once you know that your y is -3, you know that coordinate 2, -3. Let's graph the coordinate 2, -3. So 2 on the x, -3 on the y. That's down here. We might as well jump into the axis of symmetry. That'll be the equation x equals the x value of your vertex, which is 2, right? We found that x is 2 of our vertex, so x equals 2. That will produce a vertical line crossing the x-axis right at the value of 2. I mean, you didn't have to write the equation to know that, because the vertical line that passes right through the vertex is your axis of symmetry, and it will be x equals the x value of your vertex. Now, we need more coordinates. So you could use an input-output table. How about the easiest coordinate to find would be the y-intercept? That would be 0, the c value. So what is the c value here? 5. So my y-intercept will be 0, 5. So you could actually go to the coordinate 0 on the x, 5 on the y, that's right here. So I know that this is a point on my parabola. If I were taking a multiple choice test, I would already know that my vertex is here and that it has to open up passing through that point, so I'd already be able to identify the correct parabola. But right here, we want to find more points. So maybe instead of using an XY table, we could use the pattern and modify it, because we can't use the pattern as is, 1, 1, 2, 4, 3, 9, because that is for the A value of 1, and obviously we have an A value of 2. So because we have an A value of 2, we need to modify the outputs. So we've got to multiply that by 2, the 4 by 2, and the 9 by 2. Then it'll give us 1 times 2 is 2, 4 times 2 is 8, 9 times 2 is 18. And now we could use this new modified pattern. Instead of 1, 1, it's 1, 2. Instead of 2, 4, it's 2, 8. Instead of 3, 9, it's 3, 18. So what does that mean? That from this vertex, I want to go 1 to the side and 2 up. Why up? Because it's positive. So 1 to the side, 2 up, put a dot right there. Whoops, red dot. Yeah. And 2, 8 will get you 1, 2 over, 1, 2, 3, 4, 5, 6, 7, 8. I'm right here on the edge. And of course, going 3, 18, 3 to the side, 18, you're going to be way off the graph, so don't do that. I mean, you could if you wanted to, but you don't need to. So just map those points over to the other side. This one's 1 unit away, so go 1 unit this way and put a dot right there. And this one is 2 units away, but we already have that one because we knew that the y-intercept was 0, the c value. There it is. So there's our perfect parabola. Yeah, it got a little narrower than the original parent graph because the a value is 2. It got vertically stretched. Now, let's say you didn't want to deal with the pattern. Let's say you wanted to stick with the input-output table. You could do that if you want. You could plug in 0, and you will get the output 5. That was the y-intercept. You could plug in the number 1. And if you did plug in the number 1 into here and here, into the x's, think about this. 1 squared is 1. 1 times 2 is 2. 8 times 1 is 8. 2 take away 8 is negative 6. Negative 6 plus 5 is negative 1. So when I plug in a 1, I get out a negative 1. And you will see that 1, negative 1 is that blue dot right there. So I think it's a lot better to use the pattern and modify it if necessary. But you could always use an input-output table if you really wanted to. Final couple of things that we could state on number 3 is the domain and the range. What's the domain of this parabola?
X equals all real numbers.
X equals all real numbers. And you have to say X equals. If you just say all real numbers, technically you're not giving the full answer. How about the range? The range are your Y values. Where does this parabola? Greater than or equal to? Negative 3. Excellent. Y is greater than or equal to negative 3. Perfect. So with that said, we're going to stop right here. It's been a long lesson. I apologize, long video. Tomorrow, we're going to continue working on these practice parabolas, and we'll even do some that have fractions in them. We'll pick this up tomorrow.